directly to my battery. And in this plate here then, this other contact, we'll look at the relays here in a second. But this relay then is going to go down to my armature of my motor. So what happens is that I turn on my ignition and it's very low current. It takes very little bit of current, energizes coil. This coil then energizes, that shaft pulls forward, it engages the sprocket into our flywheel, and then at the same time, these two contacts are like a switch. Those two all of a sudden close together, and then I get my full current going through my contacts and then down to my starter, and then that's what engages that's what starts to turn my starter over. So this on a car, it actually acts like two things. It acts like a electromechanical device where it's engaging our flywheel, and then it's also acting like a relay, and it engages our high current going into our starter. So when I turn on my ignition, this thing might only take maybe about 1 amp of current to engage that solenoid. Once that solenoid engages my starter, then I'm drawing about close to 300 amps off my battery. That's about how many, it takes anywhere from 150 to 300 amps depending on your side of the vehicle. That's about how much current it takes to start spinning that motor and turning your engine over. Well, my ignition key can't handle 300 amps of current going through there. If I were to put my starter motor directly into my ignition of my key, and I tried turning that starter over directly without a solenoid or a relay in there, I'd be drawing 300 amps of current going through my ignition switch. Most likely I'd end up burning up the contacts that are in my ignition switch, or it would really heat up awful hot there and would end up burning out my switches. So that's what we use our relays for, is to switch very low current into very high current. And we're going to take a look at the lab here. That's for lab 7. We're going to take a little bit more look at the relay there. So those are a couple of devices that we see all the time in our field there. So a lot of times we might be just using this to engage some other type of device in our automation equipment. And then relays we can use either to control things or use them as logic. So let's, somebody happen to have their parts kit with them with their relay in there? I don't have that part number for that relay. So let's take a look at the relay here.
You have the number. 12 volt DC, double probe.
You know what they're looking for. You know what your relay looks like.
This thing?
Oh, this one here. Here's your relay that came supplied with your kit there. So that's the one that if you have your parts kit, you can dig that out. And I'm gonna. Then if you have your lab manual, we're gonna take a look right at your lab, because that's a little tricky. That there's a little circuit there. So you're gonna go through the lab, and then when you get to the further investigation, you have to design your own circuit on page 123 of your lab manual. So basically, what it is that this relay that you're looking at right here consists of a coil and then a switch. And it has either a normally closed switch, which is the top one, and then the normally open contact. basically what it is we're going to have our DC power supply. And typically when we're drawing up symbols for our relays in our schematics, we draw it up as just a circle. And then typically a lot of times from the old days they're called CR1s, meaning that it's a net represented as a control relay. And we would number CR1, CR2, and go down the list as however many relays we had in there. So a lot of our equipment way back in the prior to the early 80s, a lot of our equipment was all done with what's called relay logic. Instead of PLCs, programmable logic controllers, or microcontrollers, all these solid-state devices, or even transistors, we used to use mechanical relays. And then these would come out of our circuit boards or whatever, and then we can control our different devices. So this is the coil. This is make up for my coil. And then what we would do then is, and I'll draw a little bit simpler. So then we might have another source. And we'll just say we're turning on a light bulb. And then we would, then we could call that one. So then we'd also name that contact CR1. So what it did is it tied this coil to this contact. So this one would say that this one's CR1, but this is a normally open contact. So right now, if I don't apply, if I have a switch here, let's put a switch in. If I have my switch open, I'm not energizing my coil. If I'm not energizing my coil, my contacts stay normally open. And we'll say this is 5 volts DC, and we could say that this is 120 volts AC. So then what happens is that here I got this control relay. It's being controlled by 5 volts DC. I go ahead and I close my switch. I energize that coil, and it's going to pull this contact. It's going to form a magnetic field there, and it's going to pull this armature down. It's going to try doing like a magnet. It's going to try pulling this armature down, and then it's going to make contact with my normally open contact. And then this contact is going to close. So then also now I got a current path going through there. Now I have 120 volts AC. 120 volts AC going through there, and now I'm connecting my path, and now all of a sudden my light starts to light up. Okay. This here, depending on the resistance of the windings, might only draw anywhere from, might draw only about 20 milliamps of current. Here I could have a really big, heavy-duty light bulb or something, and now maybe I'm drawing, 2.5 amps. Okay, so I can take my switch. I can have just a very small signal switch that doesn't have to handle very much current, just a really lightweight switch. I close that, energizes my coil at about 20 milliamps of current, and then it's going to close this contact, mechanically close that contact. My current's going to start to flow, and now I'm drawing 2.5 amps of current going into my main controlled circuit. So I can take very small signals coming either out of a lightweight switch, or it might be coming out of a printed circuit board that can't handle much current, and switch very large amounts of current. Some of these ovens and stuff, they got hundreds of heating elements in there, and we could be drawing anywhere up to 500 amps, on these big industrial ovens and stuff. And I could control a 500 amp oven with just 20 milliamps of current. But on the secondaries, the size of where my contacts are, that can be drawn as much current as I need to, as long as I size my coil the right way, or size my relay the correct amount. So it's just one way of us for being able to take small signal and control very large amounts of current. All right, so let's take a look. Open up. Let's take a look at the lab here, and then show you how I had approached this problem here. So here's our further investigation on in our lab manual. So what they want you to do is that I got two LEDs. These LEDs are solid state devices, and they only allow current to flow in one direction. So for example, on the LED where the red one, this side has to be more positive than this side. This side has to be more negative. This is called my anode, and then this is called my cathode. So this is what we're going to get into when we get back from break. We're going to be looking at these solid state devices. On the other LED, this one here wants to be more negative, and the anode needs to be more positive than our cathode. So that they're only going to light up in one direction. So I have a series parallel circuit is what I have. I have this 330 ohm resistor, and then I got two LEDs that are in parallel. So if I were to straight line that up, sometimes, like I said, sometimes it's just easier to straight line your circuits. So here's my 330 ohm resistor. And what they want us to do is that when on my coil of my relay, when I'm at rest, when it's not sitting, let's see which one do they want lit up. When the switch is closed, the red LED. So this one's going to be with my switch closed. So this is going to be with my coil energized. So sometimes we just kind of make little notes on our schematic so we know what's going on. And when it's open, the voltage should reverse, causing the green LED to turn on. So then this one is coil not energized. So what I would do is I would first approach take a look at what it is that I need to do. So I know that, since I know that my polarity of my LEDs are going to determine which LED is going to be turning on, then I know what I want to do is that I want to switch the polarities of these legs here. If I put this one, if I make this line here more positive and this one more negative, and we'll say this one's my red LED, this is my green LED. If I have this one more positive and this one more negative, which LED is going to turn on?
Red.
So,
Isn't it the red
which one?
The red.
The red one. Because this one here is going to be, because if I do my current paths and polarities, I know this is going to be, even I don't know the voltage, I know that my current flow is going to go this way, right? And it's going to come up, and it's going to try to split. Some of it's going to try going that way, and some of it's going to go this way. These LEDs kind of act like switches. If I put my polarity across here, negative positive, I've got the reverse polarity going across this LED. And that LED is not going to turn on because I got the reverse polarity on there. So it's acting like a switch. So that one's just going to act like an open, it's not going to turn on. But then, so my current here is going to go across here. This one's going to be more negative, this one's going to be more positive. And now, since, just like I said, as long as my cathode is more negative than what my anode is, then that LED is going to act like a switch, and that's going to turn on, and then it's going to light up. And then so all my current is just going to go, this one's going to act like an open, it's not even there. My current's going to start to flow through the LED, light it up, and then the current's going to come back up to my resistor. One thing about LEDs is that they always take their voltage first, and they'll take as much current as you give it. So sometimes we have to limit our current going through an LED. And we use that by here. This is what we call our current limiting resistor. Remember the two things what are the two things that we can use a resistor for? One is for limiting the current, what's the other use for resistors? Especially if I wire them up in series.
Divide the voltage.
Divide the voltage. Those are about the two main things that we use resistors for. We either use them for current limiting or we divide the voltage. So this current limiting resistor is to limit the amount of current that we got going through our LEDs. Typically our LEDs like about, for a standard LED, we can run about anywhere from 20 to 40 milliamps on them. So we'll just say, so we don't heat them up, we'll just say 20 milliamps. Say that we want 20 milliamps of current. Remember now, this LED is not even in the circuit because that's acting like an open, so we'll just go ahead and we'll get rid of it. So now we just have ourselves a series circuit. We know that LEDs also have a voltage rating. So we'll just say that it wants to take 2 volts to light up the LED. It wants to take, it's going to want to take about 2 volts. Did they say what? Yeah, so they're just going to use our 5 volts. Is that what our relays are? 5 or 12?
5 volts.
They are 5 volts? Okay. So we know that I'm going to have a source voltage. I know that this is going to be, my voltage drop across here then is going to be 5 volts. That's what we're going to be using for our source voltage. We know the LED is going to want to take its voltage first, and it's always going to take 2 volts of that 5 volts. The remainder is going to drop across the resistor. And so the resistor is going to drop the remaining amount of voltage, and that's going to drop our 3 volts. So then if I'm going to do, I should gave the current because they already gave us our resistance value. So now if I take my 3 volts and divide it by my 330 ohm resistor, how much current do I have going through that resistor?
$9.09 milliamps.
9.09?
Yep, 091.
091 milliamps. So that's how much current is going through the resistor, and since I have a series circuit, then that means how much current do I have going through my LED then?
9.091.
Yes, 9.091 milliamps of current going through there. And that's how we limit our current. We don't want to ever, otherwise that LED will take as much current. If I put that right directly, if I put an LED right across the battery, it's going to try drawing as much current as it can until it burns out. So if I hook it up to a 5-volt source directly, it's going to act like a dead short across my battery, take as much current. It's going to light up for about a brief second, then it's going to burn up. So that's this is the stuff that we're going to be getting into next semester here. So if it doesn't quite catch on, don't worry about it. They already gave you the values that they wanted you to use and stuff like that. So the big thing is that we're going to go back and we're going to put our other LED back in. The one with the line has to be more negative than this one, and this one's going to be our green. So now I know when I'm positive and negative in this polarity, the red one's going to turn on. Then what I want to do is I want to turn the green one on. And so then what I have to do then is I have to come up with a way of switching the polarities. So now this time I'm going to switch it to negative positive. This time now my current's going to flow this way through my resistor, and it's going to come down. And it's going to come by, and this one's going to be, this one here now is going to become more negative on my anode side and more positive on my cathode side. This current here is going to go through, and this one's going to be negative, positive, and then back to here. So now I'm more negative on my anode, and then LED is going to do what?
Act like an open.
Act like an open. Perfect. That's exactly what we have to. So that one's going to act like an open, and the green one is going to act like a what?
Switch. Short.
As a short, like a switch. That one's going to short out and turn on, and then it's going to allow the current to go through the green one this time, and nothing going through the red one. So the red one's going to turn off, and the green one's going to turn on, and then my current is just going to come back and go to my positive side of my source. Okay, so that's always our first thing. First we got to analyze what's going on with our circuit, and then we can go and figure out what to put in here, because now we know what we need to do. We know that we need to switch it from negative to positive. Go negative to positive one way, and positive to negative the other way. So we have to come up with a way of doing that. And this is a little tricky until you really start getting into, using some programming and stuff. But whether if it's relay logic or programmable logic or using LabVIEW, the concept is all the same. We're turning on and off different things. So what we're going to do is we're going to take a look, and there's no real easy way of having you try to solve for it. This is actually a lot tougher problem than what it appears to be. So we know that one time here we're going to do our positive, negative, and then when we energize the coil, then it's going to switch polarity, and then it's going to go negative, positive. Here I have, these are my two common things to the circuit. I have two wires that are coming out, and those are my commons. So what we're going to take a look at is here's our contact configuration. And when I'm looking at these contacts, and we're going to pop up the data sheet from our coil, from our relay. But I have my number 2 pin. That one's going to be my normally closed contact. My number 3 is going to be considered my normally open contact. And this number pin 1 is this is what we normally call our common. That's what you'll see on your data sheets typically. This one here is common to both pins 2 and 3. 2 and 3 have no correlation with each other. They're totally separate. But pin 1 does have a correlation with pin 2. And if I energize it, then it has correlation with pin 3. So that's our common. It's common between both pins 2 and 3. But 3 has no correlation with pin 2. Those two, I would never wire up anything just to pins 2 and 3 because they would always act like an open. So I know that here's my 2 lines that are coming in. What I'm going to do is I'm going to attach these ones to my common side of my contact. So here's my contact, and that's going to be going to my relay contact. So the blue is my relay now. And then it's going to, then the common then has that armature on there. And then it's going to make contact. When it's not energized, it's going to make contact with this one. So according to this schematic, we're going to.
You want the relay pin numbers?
Not yet. We're going to pull up the data sheet. So we're just going to use what's on the board here right now. So the pin numbers that we're using now are just related to this one here. What Bob's talking about is the actual relay pin numbers. We're going to take a look at that later. So our pin numbers are going to change slightly when we go into a real relay. So this one here is going to be our pin 1. And this one's going to be pin 1. So what they have is, because we're using a double pole, double throw, we actually have 2 sets of contacts. Pins 2, pin 3, and pin 1. So these are both electrically separated. This is going to be my contact number 1. This is going to be my contact number 2. Okay. When I energize the coil, it's going to energize this one and it's going to energize this one both at the same time. I've got 2 separate contacts. So that's what we're using is a double pole, double throw. That's what we have in our parts kit. And so these are both mechanically tied together. And a lot of times you'll see it with a little dotted line on there, representing that these 2 are mechanically tied together. So if one switches, so does the other one. So this one here is going to be our pin 1, that's our common, and then we have our pin 2, which is our normally closed. And we just abbreviate it as NC, normally closed. So there's our pin number 2, NC, number closed. Now, what we need to do is that we need to make, so we're going to look at the red one here first. We need to make this one more positive and this one more negative. And I'm going to kind of do it, how do I want to do it? Let's try doing it the way we see it in the schematic. In our schematic, I'm going to try making it simple here. In our schematic, we might just see a little source. Then it's just going to say that here's my battery source, my negative is my common, that one's going to be my reference point, that's going to be my ground. And then my positive side of my battery source is going to be my plus 5 volts. And another way that we look at it in our schematics is what they just do, is they just do this. They just make a little, like a little T symbol, and they just say plus 5 volts. When they do that, we always know that my reference point is going to be, my negative side is going to be my reference point. That's going to be going to my ground. So a lot of times we'll just see the symbol that looks just like this on our schematics. They actually hand out your schematics to you yet? Yeah, so on there you can kind of see that on the, I'll pull it up here real quick so you can take a look at it so you can start getting familiar with the schematics here. So you can see right here, this first part of that circuit that's in on my wave tech, this is my power supply. And so you can see here they're just saying, here's my plus 5 volts, and here's my negative 5 volts. And then my ground is going to be right in between the two. Okay, so right now we're just looking at a single-ended, what we call a single-ended power supply. It only has one voltage and one ground. It doesn't have a negative and the positive 5 volts. It's just going to have a positive 5 volts and a ground. And then throughout a lot of the schematic, then they'll just, let's see if I can find one here. Yeah, here we go. So this one has multiple voltages, but you can see that they're not drawing in the power supply every time. They just go ahead and they just say this is going to plus 15 volts, and it's going to R62. It's being represented this way. In our heads, we know it's logically wired up this way. But they're just showing you that this is going to be at plus 5 volts. So that's what we're going to do on our schematics here, to make our schematics a lot easier. Instead of drawing up all our power supplies, we're just going to draw in our power supply. So there I know that this one here is going to be, has to be more positive. So this is going to be my plus 5 volts DC. And then this one here is going to have to be what?
Ground.
My ground. And so this one here is going to go to my ground. So then if I'm not energized the coil, pins 1 and 2 are making contact. That's acting like my switch. God. So I know that here's what it looks like. I can go ahead and draw the same thing in. This is what it would look like if I actually drew in the whole power supply. That's what it would look like. And then here's my 5 volt source. But we don't draw that. We don't draw in our power sources every time. So then what happens then is my current is going to come onto my negative side. It's going to go through my contact with my relay, come up, go through. We know that it has to be more negative on this side, so then my red LED is going to turn on. This one's going to turn on, green one's going to stay off. It's going to come up, go up to my current limiting resistor, back, through pin 1, up to my normally closed, and then back up to my source. So now I just turned on my red LED. Okay, so now I'll show you why we don't draw in all our power supplies every time. Now, so we got the first, what they wanted. They said, I think they actually, they had it energized to begin with, but that's fine. So we got one condition made. When it's not energized, the red LED turns on. Now what we want to do is we want to do it the other way. Now we're going to switch our polarities. Before this one was hooked up to our plus 5 volts. Now what we want to do is make this one more negative and this one more positive. So what we're going to do is we're going to tie pin number 3 to what?
Ground.
The ground. And then this pin 3 of our relay is going to go to what? So it has to be more positive, right? So that one's going to go to our plus 5 volts DC. So now all of a sudden I energize that coil and pull these two contacts down. And now what happens is that now this is my ground, this is my more negative side, the side here. This is more negative, and so now my current is going to start to flow in the opposite direction. Now my current is going to flow this way, come down, negative, positive, go down through this relay here, negative, positive, back down, and then back into my plus 5 volts DC. Okay? So all we're just doing is we're taking those two contacts and we're switching the polarities. This one, when it's not energized, my normally closed contacts are going, brings this one to be more positive, this one more negative, turns on the red LED. I energize the coil, I switch the polarities of my battery, just like me turning my battery back and forth, flipping it around in my circuit. Flips it up the other way, now this one becomes more positive, and this one becomes more negative, and then it turns on my green LED. So now I just showed you how to wire up that whole further investigation, but I'll tell you the challenge will still be just wiring that thing up.
Absolutely.
Yeah, it's tough. Alright, does that make sense to what's on the board?
It's a solid picture.
Huh?
I wish I got that picture when I was.
Yeah, no, it's hard to get that picture. So you guys that do it earlier, you guys got to work at it a little bit more, but that's why I had to help. That's why I had to kind of get you going, because that's to understand how to hook those up, that would have been nearly impossible unless you've been in the industry. That's not an easy task to do. Yeah. But it's good to challenge yourselves doing this just to see if you can come up with something. But that's a tough circuit. I was kind of like, it seems very simple, but and straightforward. But man, trying to get that picture in your head, that's tough. All right, so let's take we're gonna keep this schematic up, and then we'll fill in our. And then even to know how to draw the thing up, that's tough too. Just knowing how to draw it up. This saves you a lot of. One thing you can see too that when you're drawing your symbols, typically we always draw them vertically. All our symbols are always vertical. So you can see that my plus 5 volts always comes up and it sits up this way. My ground, I come up and I come back down. I don't ever want to do this. Makes for a very chaotic. You never want to draw your symbols upside down. So what you always do is you draw them always right side up. Even if you have to come over and bring them back down, drop back down this way so that all your symbols are all facing the same direction. Alright, so let's take a look. I didn't have the part number, so I haven't been able to. Did you find this on DigiKey or just a random Google search?
We talking about the schematic?
Yeah, for the.
I found it in DigiKey.
You did find it in DigiKey?
Mm-hmm.
Okay, yeah. So let's use. So what we'll do is we'll go to DigiKey. And what I'm going to do is I'm just going to do a product search. I'm just going to. The manufacturer on these relays are made by Chirac.
It actually going to just product index with you, and then it'll give you the company that's made by.
What's that?
You get the product index, it'll give you the company that's made by.
Yep. Otherwise, we can do a lot of times. We can just do a. So what we're going to do is we're just going to do a vendor search here. I can read it here. But yeah, you can go do it that way too. So I'm going to have to write this down. Here. You got good eyes? I don't know what that part number was. I think it's like RP. RPA. Sorry, that's right. So we'll try doing that first. So I'm just gonna. So I know it's been made by So the first thing I'm going to do is I'm just going to try narrowing my search as much as possible. So I'm just going to put in the part number and see if it comes up with anything. RP 82101. See if it by any chance finds it. Now look at that, there it is. Came right up. Okay? So all I had to do was put in the vendor's part number. I just put in this part number in my search and it automatically came up with my relay there. It's in our parts kit. So now what we use is we're going to start getting, especially next semester, we're going to be starting to use our data sheets a lot for all our components. We haven't had to do that with our resistors and stuff, but if you've already had digital, you've already know how to do data sheets, but if you haven't had digital yet, you'll be introduced to data sheets now. So we're going to open up this, so all I'm going to do is I'm just going to go down and where it says data sheets, I'm going to just open that up. Then I'm just going to open it up in my PDF. And then it kind of tells us some things about it. You know, it's a 2-pole, 8 amps. Two form C, I don't know what that. I think that CO represents common, or no, that should be our normally closed. But that would be our normally closed, and then our 2 forms of normally open contacts. I'm not too sure what the abbreviation CO stands for, but it represents that it's 2 normally closed contacts is what it is. But this thing can handle, on the contacts itself, this thing can handle 8 amps of current. But that's not how much current it's going to take to energize the coil. We should be able to find that. Coil voltage range. So we should be... well, here we can kind of figure it out. If we look at our 5 volts DC, we know a couple of different things. We know we can figure it out either by using our power or our coil resistance. But we know that it's going to be 5 volts, and it's going to have a resistance of 54 ohms. So what's 5 divided by 54?
About 10 amps. 10
Well,
milliamps.
that's coil resistance. That must be in. That can't be in ohms. What's 500 milliwatts divided by 5?
Did you forget?
So, because if we have P is equal to,
Kurt, did you forget to have them buy calculators?
I looked
I
at
don't
it.
see a calculator out.
So we want to leave our current separated. We just take our P divided by E. So if I take 500 milliwatts and divide it by 5, what do I end up getting for current?
100
It's got to be
milliamps.
100 milliamps. You're only off by 1,000.
I knew someone was wrong when they said 10 amps. No coil ever does 10 amps.
No, but well, here's why. Because we went by the coil's resistance and the coil voltage.
10 milliamps.
But it says 54. But that must be like that must be in.
It still wouldn't be 10 amps, would it?
No, 10 milliamps.
10 milliamps.
10 milliamps. Oh yeah. So
And that sounds low.
100 milliamps. Yeah. So about 100 milliamps. So I can switch up to 8 amps, but it only takes 100 milliamps of current to turn it on.
Hey, Kurt, can I interrupt just for a second?
You always interrupt.
I know.
Only if
Why
we
did you ask this time? They don't have something important this time.
I figure they're all...
He's serious now.
only if we can put you on video.
Oh,
Yeah,
no.
that's right.
Well, if I go get a hair job over winter break, then maybe you know. I would have got one this weekend, but the lottery didn't come through.
Yeah, sit down, I'll take care of you. What is the old-fashioned way?
I was looking at our schedule for the spring. Few people still haven't signed up for the LabVIEW class of computer control. There's at least 3.
Did you see
You're one.
Did you see who the instructor was?
Where's Ross? Ross is one.
No, he's not in my class. Not till next spring. He's in Dan's class.
Oh, to get Ross.
He's a spring
Luke-
start.
Luke too, probably. I'll have to get
Yeah,
him.
Luke Ogren.
But a few of you haven't signed up. Here's the reason I need you to do that. I'm ordering the books before, there's a lab fee priced in because we're using different books this week here, and these are non-resellable books. That's why there's the lab fee in there. I'm going to order the books probably on the 19th, and I'm thinking anybody who's not on the 19th, I'm going to close the class down, and then you're just shit out of luck. Okay? Because it takes a few weeks. These books are made on the spot. Okay? So if you're planning on taking that class, I didn't see you on there, or did you not do it yet? And I don't know a lot of people in here yet, so I don't know if they're on it or not. But please get that done. Make sure you get your math signed up, 1,400. Make sure you get all your classes in, because a couple of classes, I got a list of people who want to come in this spring, and I'm either going to open it up for them, which then could turn around and take your spot, okay? Especially with the possibility of the lab, even the digital one. Second thing, for all the people in digital one in the evening, instead of showing up tonight, when you go in the lab this week?
The rest of the week.
The rest of the week. Do you want to just show up to lab tomorrow, we'll take the parts and I'll check you off that you turned the parts in and turned the boards in instead of showing up tonight? And then I'll individually talk to anybody who, if you get a good grade on the final, could raise your grade. Some of you, you're so solid on the A, you would have to get a 0 on the final in order to drop down to a B. Why test them then? Right?
I think that's fine.
Do you think I could make a test hard enough that he gets a 0 on?
Question sheet with no questions on it.
Yeah.
Here, fill in the answers.
Write the test.
There you go.
You got 1.5 hour. Okay, so for the people who are in digital, okay, and then I'll take care of, we have 3 or 4 people that aren't in here. I'll just take care of them tonight. Otherwise, the whole night is turning in the parts, turning in the boards, getting checked off, which I have to go one student at a time. So whoever's at the end of the alphabet will be there for an hour and a half. So would you rather do it that way? We just do it during lab. Well, you're during lab. I'll just I'll have you move your parts, and then I'll have one person at a time bring them up, turn them in, put the boards away, and then I'll tell you what your grade is, and we're good to go. Is that how you want to do it?
Sorry, I got my own board at home, so you just need the ICs back that you gave us?
Right.
Okay.
Now, when you pop them out, though, be careful so you don't bend the crap out of it.
Yeah.
Yeah, I need the LEDs.
What do you
because-
carry?
Yeah, the ice. If you didn't check out the board, then, yeah.
You just gave us that one LED, right? The other one was our own.
Well, a few of you burnt some out, and I gave you one.
Okay.
So the ones that did, if you did burn out your own, I'm okay if you keep the one then. So because you might need it this spring.
I think you said, where do you say you did
So,
900?
is that how you guys want to handle it? Because I know you drive a long ways,
Just like I
I
talked
know
to
you
you.
drive a long ways.
Yeah, you're going to do the pre-calc.
Take care of it in class tomorrow?
Yeah, ignore Tom, yours.
All right.
Yeah, you're in good shape.
That's all she wrote? We're done?
We're done.
Sweet.
We're done. I'll just talk to a few that are on that iffy, that borderline one way or another, and I'll give you guys a shot to improve it.
Cool. All right, sweet.
950, same thing. You can go right in.
Man.
Only take 1,400 if you haven't done 900 or 950. So if you still haven't done, if you've done 801, then you need to either take, then you can go into 1,400. If you already done either 900, 950, or 1,400 already, you can do pre-calc this summer. So don't take 1,400 if you've already done 900 or 950. Okay? So be careful of that. And then remember that 1,700 is our required math for our program to get the degree, and that's the only one that's worth a Gen X. Okay? 900, 950, 1,400, none of those go towards your 18 credits of your Gen X.
What?
Those are developmental classes.
1,400 doesn't give you 5 credit points toward your degree?
No. I heard you say that. I want to come back in.
That's